This lecture will cover acids and bases. So the first thing we're going to do is go over two definitions of acids and bases. There's more than just these two, but these are the two that are important for this class. So the first definition is Arrhenius acids and Arrhenius bases. So an Arrhenius acid is defined as a substance that dissociates into hydrogen ions, H+, and some anion when dissolved in water. So for example, hydrochloric acid will dissociate into H+ and Cl-. Nitric acid will dissociate into H+ and NO3-. Acetic acid will dissociate into H+ and the acetate ion. Arrhenius bases are defined as substances that dissociate into hydroxide ions and cations when dissolved in water. Just a note, we already talked about naming acids, so I'm not going to go over that, but for naming these types of bases, you name them as the name of the metal and then hydroxide. So for example, here this is lithium hydroxide, sodium hydroxide, calcium hydroxide. Generally, Arrhenius bases are group 1A and group 2A metals with hydroxides. So lithium hydroxide in water will make lithium plus and hydroxide ions. Sodium hydroxide in water will make sodium ions and hydroxide ions. Calcium hydroxide in water will make calcium ions into hydroxide ions. The next definition is Bronsted-Lowry acids and bases. In Bronsted-Lowry acids and bases, we're going to talk about the movement of H+ or protons. So a Bronsted-Lowry acid is a substance that donates a hydrogen ion or a proton. Just a note, free protons don't exist in water. They actually will react with water to make this hydronium ion, H3O+. When we're talking about acids and bases, you'll generally see H3O+ and H+ used interchangeably. Just know that in real life, I guess, you don't have H+, you actually have H3O+. And know that if you see H3O+ and H+, we're talking about the same thing. So some examples of Bronsted-Lowry acids would be hydrobromic acid. When you put hydrobromic acid with water, you'll make H3O+ and Br-. So HBr donates a proton to water and becomes Br-. Nitrous acid in water becomes H3O+ and NO2-. Nitrous acid donates a proton to water, becoming NO2-, and that's what makes it an acid, a Bronsted-Lowry acid specifically. Bronsted-Lowry bases are defined as substances that accept protons. So for example, ammonia in water ammonia will accept a proton from water to become NH4+, and you also make the hydroxide ion. Cyanide ions in water will make HCN. Cyanide ions will accept a proton from water, make HCN, and you'll also have hydroxide ions. In this Bronsted-Lowry acid-base definition, you have things that are called conjugate acids and conjugate bases. And basically these are pairs. So every acid has a conjugate base and every base has a conjugate acid. So for an acid, its conjugate base is whatever it becomes after it gives up a proton. And for a base, its conjugate acid is whatever it becomes when it accepts a proton. And that means that in this Bronsted-Lowry acid-base definition, something in the reaction has to be acting as an acid and something else has to be acting as a base. You can't have two acids reacting together. You have to have an acid and a base, and you actually have to have both. So for example, here we have fluoride ions in water. They make HF and OH-. So the fluoride ions accept a proton from water to become HF. So fluoride is acting as a base. It's a proton acceptor. So this is a base, and its conjugate acid would be HF. So what it becomes when it picks up a proton. Then also you have water here, right? Water had to donate a proton to fluoride ions, and it became hydroxide. So water is acting as an acid, and so its conjugate base is the hydroxide ion. If you look here at the carbonate ions, in water, carbonate ions will accept a proton. So carbonate is acting as a base, and its conjugate acid would be bicarbonate, HCO3-. Water here, it donates a proton to the carbonate ions, so it's acting as an acid. And again, its conjugate base would be OH minus. Then if we look at sulfuric acid in water, sulfuric acid will donate a proton to water. So sulfuric acid is acting as an acid. It becomes HSO4 minus when it donates a proton. So HSO4 minus is sulfuric acid's conjugate base. Water here accepted a proton, so water is acting as a base, and its conjugate acid is H3O+. One more example here is hydroiodic acid. Hydroiodic acid donates, oh sorry, that should say just I minus, I apologize. Hydroiodic acid donates a proton to water to become I minus. So HI is acting as an acid, its conjugate base is I minus. Water is acting as a base, it's accepting a proton, so water's conjugate acid is the hydronium ion. As I'm sure you notice here, water sometimes acts as an acid and sometimes acts as a base. That means it's amphoteric, that's the word for it, and that is just a substance that can act as an acid or as a base, just depending on the circumstances. Here's some more examples of conjugate acids and conjugate bases that you can look through. Okay, now let's talk about neutralization reactions. So neutralization reactions are reactions between an acid and a base. And when you have a reaction with an acid and a base, you always make salt and water. So for example, if we have hydrochloric acid reacting with potassium hydroxide, you'll make potassium chloride and water. So what happens here is you have your acid, the hydrogen ion from your acid reacts with the hydroxide ion from your base to make water. And then you make a salt of what's left over. So we have this potassium left over, chlorine left over, so we make KCl. Here's something to note. You have to do charge balance still, right? Here, potassium's +1, chlorine's -1, so you make potassium chloride, just KCl. But if you had, instead of potassium hydroxide, you had calcium hydroxide, calcium's 2+, chlorine's Cl-, 1-, so you would make calcium chloride, which is CaCl2, and you'd actually make 2 waters. So just make sure you're watching your charges between your cation and your anion that's making the salt. So the net ionic equation for neutralization reaction is H+ + OH- makes water. So the net ionic equation will actually be the same for every single neutralization reaction you do. Okay, let's talk about titration. So in a titration, we react some substance with an unknown concentration with a substance with a known concentration. And when we do this, we can actually figure out the concentration of our unknown because we will know the exact volume of our unknown. We know the exact concentration of our known and the exact volume of our known. And we can use stoichiometry to figure out our concentration of our unknown. So generally speaking, when we're doing a titration, and you can see this down here, you'll put an acid in a beaker or in an Erlenmeyer flask. And again, you won't know the concentration of this acid, but you know exactly how much you have, either number of moles or volume. Or sorry, you'll know exactly the volume, I apologize, that you have. Here, you'll have base in a burette, and you'll know the concentration of this base. And what you'll do is you'll keep adding base to the solution. The H+ is going to react with OH- to make water until you hit what's called the equivalence point. So the equivalence point is the point of a titration where the number of moles of hydroxide ions added, so the number of moles of hydroxide ions added from the burette is equal to the number of moles of H+ originally in solution. So again, we know exactly the concentration of this base solution, and we know exactly the volume we added, so we can figure out how many number of moles we have, right? Because concentration is moles per liter, and we know how many liters we added, we can multiply them together to get moles. And at the equivalence point, the moles of the base are equal to the moles of the acid in our unknown. And then from that, since now we know the moles of our acid, and we knew the volume of it before, we can calculate the concentration of the acid. And how do we know when to stop titration? Well, we use something called an indicator. So an indicator is some dye whose color is dependent on the pH of the solution it's in. So you can see here, see how it's pink at the equivalence point, but before it's clear? This indicator is called phenolphthalein. It's one of the most common acid-base titration indicators used. It changes color in a basic solution, so just above a pH of 7, and that's generally a good pH for titrations. So when you have a titration between a strong acid and a strong base, your equivalence point will be exactly at a pH of 7, neutral pH. Weak acids and strong bases, and strong acids and weak bases, those get a little more complicated. We have different indicators that change color at different pHs, and we might have to change indicators depending on what pH our equivalence point will be. And you can actually calculate the pH that your equivalence point should be and then backtrack and figure out what indicator you should use. But I think the important thing to know is that in a strong acid, strong base titration, your equivalence point will be at a pH of 7. So again, we can, like I said, we can calculate our concentration of unknown doing a titration. So let's say we have 10 milliliters of hydrochloric acid, and it's titrated with 12.54 milliliters of a 0.1 molar sodium hydroxide solution to reach the equivalence point. What is the concentration of the hydrochloric acid solution? Well, the first thing you want to do is you want to write out your balanced chemical equation, and this will always just be a neutralization reaction. So here we have hydrochloric acid reacting with sodium hydroxide to make sodium chloride and water. And you want to make sure it's balanced because we're going to use the stoichiometry from the balanced chemical reaction to calculate our concentration. So we know how much sodium hydroxide we added. We added 0.01254 liters of sodium hydroxide. Well, we can multiply that by the concentration of sodium hydroxide. So that's 0.100 moles of sodium hydroxide over 1 liter of sodium hydroxide. Now we have moles of sodium hydroxide. And then using our balanced chemical reaction, we can see that for every 1 mole of sodium hydroxide, we have 1 mole of hydrochloric acid. So we can use that stoichiometric relationship to figure out how many moles of hydrochloric acid we have. And that should be 1.25 times 10 to the negative third moles of HCl. Now, the thing to note is at equivalence points, you're not necessarily going to have the moles of acid and moles of base being equal, but they'll be stoichiometrically related. So you might have a 2-to-1 relationship, and that's fine. You just need to change that here. But anyway, so here we have 1.25 times 10 to the negative 3 moles of HCl. So now we go back and we take that, we divide it by the volume of HCl we had, which was 0.010000 liters of HCl, and we get a concentration of 0.125 molar HCl. So another thing is you want to use, here when you're doing this part, to figure out the moles of acid, you need to use the volume of sodium hydroxide you added. And then here you need to use the volume of hydrochloric acid you started with. You never are going to add these volumes together. Okay, now let's talk about strong acids and weak acids and strong bases and weak bases. So strong acids completely dissociate in water. So for example, hydrochloric acid and water will make H3O plus and Cl minus. 100% of the HCl will dissociate into H plus and Cl minus in water. So to indicate that, we use this one-sided arrow, saying that all of this goes here. There's no equilibrium going on whatsoever. These are analogous to strong electrolytes. So in strong acids, because 100% of this is reacted to make this, we know that our HCl concentration equals our hydronium ion concentration. We have a 1-to-1 stoichiometry. So therefore, if I have a 1 molar HCl solution, I know that I have a 1 molar H3O plus solution, and this is really helpful. So the strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. You need to know these. And the nice thing is here's 6 strong acids. You'll learn them, and then every single acid that's not on this list is not going to be a strong acid. It's going to be a weak acid. So it makes it really easy to learn, strong and weak acids, because you just need to learn the strong acids, and everything else by default will be weak. Now, weak acids are just the opposite. They don't completely dissociate in water, so you do have an equilibrium going on. And so we will use that equilibrium arrow we talked about last week. So, for example, hydrofluoric acid is not a strong acid. So hydrofluoric acid in water will make H3O plus and F minus, but it's going to be going back and forth. Not 100% of this will become this. So here, the concentration of hydrofluoric acid does not equal the concentration of hydronium ions, since you don't have 100% reaction. All we know is that the hydronium ion concentration will be less than the hydrofluoric acid concentration. That's all we know. You can calculate it, but that's beyond the scope of this class. So strong bases completely dissociate in solution. So, for example, sodium hydroxide will completely dissociate into sodium and hydroxide ions. So again, these are analogous to strong acids. We know that since it completely dissociates, the concentration of sodium hydroxide equals the concentration of hydroxide ions. So if we had a 1 molar sodium hydroxide solution, we have a 1 molar hydroxide ion solution. And again, this is very important and very helpful. So the strong bases, there's 6 of them as well. We have lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, calcium hydroxide, and barium hydroxide. So again, you need to know these, but the nice thing, here's the 6 strong bases. Anything that's not one of these is not a strong base. And weak bases are analogous to weak acids. They generally don't contain hydroxide ions, and they don't dissociate in water. So generally, they form hydroxide ions by accepting a proton from water. So generally speaking, weak bases are Bronsted-Lowry bases. They're proton acceptors, and strong bases tend to be Arrhenius Bases. They dissociate into hydroxide ions in water. So ammonia is a weak base. Ammonia and water will make ammonium and hydroxide ions. So the ammonia accepted proton from water to form ammonium and hydroxide ions. And again, you'll see this equilibrium arrow since we don't have complete reaction. So again, just like with weak acids, the ammonium concentration does not equal the hydroxide concentration. All we know is that the hydroxide concentration has to be less than the ammonia concentration. Okay, let's talk about pH. So the pH scale goes from 0 to 14. pH of 7 is neutral, so pure water has a pH of 7. Anything less than 7 is acidic. Anything greater than 7 is basic. So how do we calculate pH? Well, it's pretty straightforward. So the pH is equal to the negative log of our hydronium ion concentration. So let's see, let's calculate the pH of a solution that has a hydronium ion concentration of 1.5 times 10 to the negative 7. So we just plug that into our equation. Our pH is equal to the negative log of 1.5 times 10 to the negative 7, and we get an answer of 6.82. This solution is acidic because the pH is less than 7. When we're doing significant figures for logs, if you take the log of something, the number of decimal places you'll have is equal to the number of significant figures you have in this part of what you're taking the log of. So here we have 2 significant figures, so I should have 2 decimal places in my answer. What if I want to calculate the hydronium ion concentration? Well, that's pretty easy. So we take the hydronium ion concentration. That is equal to 10 to the negative pH. So just the anti-log is what it's called. So we want to calculate the hydronium concentration in a solution with a pH of 4.80. So our hydronium ion concentration is equal to 10 to the negative pH, which is 10 to the negative 4.80, which is 1.6 times 10 to the negative 5th molar. When you're doing significant figures here, The number of significant figures in your answer should be equal to the number of decimal places in whatever your exponent is here. So here we have 2 decimal places, so we have 2 significant figures. POH is analogous to pH. POH is the negative log of the hydroxide ion concentration. So when we're talking about pH, we're talking about a scale that's related to the concentration of H+. POH, we're looking at it relative to OH-. So we want to calculate the POH of a solution with a hydroxide concentration of 1 times 10 to the negative 3 molar. So our POH is equal to negative log of 1 times 10 to the negative 3, which is equal to 3.00. This solution is basic because it's opposite of pH, right? If we have a pH less than 7, it's acidic. A pH greater than 7, it's basic. With POH less than 7 is basic. POH greater than 7 is acidic. If I want to calculate the hydroxide ion concentration for my POH hydroxide ion concentration is equal to 10 to the negative POH. So let's say we want to calculate the hydroxide concentration of a solution with a POH of 8.55. So our hydroxide ion concentration should be equal to 10 to the negative POH, which is 10 to the negative 8.55, which is 2.8 times 10 to the negative 9 molar. We can actually go back and forth between pH and POH. So the pH plus the POH should equal 14. So if I have a solution with a pH of 5, my POH should be 9. So 5 plus 9 is 14. And again, you just have their flip scales. So again, a pH less than 7 is acidic, but a POH less than 7 is basic. pH greater than 7 is basic, but a POH greater than 7 is acidic. And finally, we're going to talk about buffers. So buffers are solutions that resist changes in pH upon the addition of small amounts of acid or base by neutralizing that acid or base. Buffers are composed of a weak acid and its conjugate base, or a weak base and its conjugate acid, both present in significant amounts. So it's very important. They have to be weak acids and weak bases. And the other very important thing is significant amounts. So when you make a buffer, let's say I want to make a buffer with acetic acid and acetate ions. Acetic acid is an acid, acetate ions are its conjugate base. I would actually take both of those and mix them together in solution. So I might take 10 milliliters of 1 molar acetic acid and 10 milliliters of 1 molar sodium acetate and put them together in water, or mix them together. Because you really want the acid and conjugate base, or the base and conjugate acid concentrations or amounts to be fairly equal. That makes the buffer work at the best capacity. And you need both in significant amounts, because if I add an acid to the buffer, the conjugate base is what reacts with it to neutralize it. If I add a base, the acid reacts with it to neutralize it. So we'll show you more in the next slide. So just like I was talking about on the previous page, we can make a simple buffer by mixing acetic acid and sodium acetate. And so if I add a base to this buffer, so if I add sodium hydroxide, it will react with the acetic acid to make water and sodium acetate. If I add acid, it reacts with the acetate ions to make Cl- and acetic acid. So that's how they work. And you can definitely overwhelm a buffer by adding too much acid or too much base. There's a point where it can't neutralize that acid and base, but you can add a fairly significant amount. Buffers are really important in our body. Our blood has a buffer in it with carbonic acid. And that's really, really important because our blood is about a pH of 7.4, and it really needs to stay very, very, very close to that pH. If it gets outside that pH, and not far outside of that pH, we're talking like pH of 7 or pH of 8, that will kill us, right? So what the blood buffer does is it keeps our blood at a pH of 7.4. So if something that's acidic ends up in our blood, it will be neutralized and the pH doesn't change. If something basic ends up in our blood, it'll be neutralized and our blood pH doesn't change. So buffers are very, very, very important things in our bodies, biologically.